Okay, in this video, we're going to discuss how cell potential from our voltaic cells connects to the concept of Gibbs free energy. In previous lectures, we talked about how we can calculate the cell potential of a redox reaction. And if that cell potential is greater than 0, that redox reaction is spontaneous. And there could be a spontaneous flow of electrons that we can use to do electrical work. And we also know for spontaneity, delta G for a reaction is negative. But we can actually quantify the connection between these two explicitly. Spontaneous redox reactions provide a positive cell potential and negative Gibbs free energy. And we can calculate, as we talked about in the past, our cell potential from the cathode and anode, or where reduction is taking place, versus oxidation. And really, we can expand this out of voltaic cells to all redox reactions, whether that's in a voltaic cell or happening in the human body. We can still make this connection of cell potential to spontaneity. And since we know Gibbs free energy is the measure of spontaneity, this positive cell potential must correspond to a negative delta G. And we actually have a precise formula for that. We can calculate the Gibbs free energy based on the cell potential, E, with this formula, negative NFE, where N here is going to be the moles of electrons transferred in that balanced redox reaction. Okay, you just get this from the counting the total electrons that are flowing away from the thing that's getting oxidized or flowing to the thing that is getting reduced, right? So if there was some reaction zinc 2 plus and on the right it was zinc 0, then there's a total change of charge of 2. 2 electrons are involved. For 1 mole of reaction, we would say there's 2 moles of electron there, and N would be 2, for example. F here is Faraday's constant, 96,485 coulombs per mole. So a coulomb here is a joule per volt. And our cell potential E is in volts. So that is going to leave us with delta G here in joules. And if our cell potential is positive, meaning it's spontaneous, and we also know Faraday's is positive and the total electrons transferred is going to be not negative, it's going to be positive, then all those positive numbers with this negative sign out front means that delta G is negative for a positive cell potential, right? Which is what we said up here at the beginning. A positive cell potential is spontaneous, and delta G is negative for spontaneous things. So that checks out. Now, we've previously related delta G to our equilibrium constant K. Delta G is negative RT ln K. And now we've added delta G related to this cell potential for redox reactions. And so if we had an E, we could turn it into a delta G and then turn it into a K through these two equations we've now learned. But we can also just do it in one step and combine these two equations to relate cell potential directly to K, and that's what we have down at the bottom. So let's take a minute and try to calculate how all these things are related using these formulas. To calculate delta G and K based on a cell potential that we're going to get from our standard reduction potential table for this reaction that is given. Okay, so feel free to pause the video here, try to calculate E cell for this given reaction like we've done in previous videos using that reduction table down below. And then you can use the pertinent equations here to turn that E into a delta G or turn that E into a K. So feel free to try that now before I solve it. Okay, so here's the balanced redox reaction. And I'm going to look down below for silver here and find silver plus and silver solid. So I'm going to be using that. And just to double check what's happening to silver here, it's going from 0 to plus. So that is or plus 1. So that is oxidation. So that is anode. So this number is going to come second in my formula for cathode minus anode to get my cell potential. What else is involved here? O2 and H plus and H2O. So that looks like here. That is my cathode, where oxygen is going from 0 to -2, gain of electrons. So that's my reduction, my cathode. That number goes here. So 1.23 minus 0.80 is my cell potential here of 0.43 volts. All right, so that is my E cell. Remember, I don't care about whatever the stoichiometry here is in terms of silvers. This is 1 silver in the table, and yet there's 4 up here in the reaction. Doesn't matter. It doesn't affect how I calculate cell potential. It will come into play now that I'm going to calculate delta G. Delta G here is going to be negative N times F times this cell potential I've just calculated, where F is Faraday's constant, 96485 joules per volt mole of reaction. The cell potential here, 0.43 volts. And then I need the moles of electrons here. And so now I need to come back to this balanced redox reaction and figure out how many electrons are being transferred. And so I'll just take maybe silver that is going from 0 to +1. But there are 4 silvers. So 1 electron is leaving silver, and there are 4 total silvers doing that. So that's a total of 4 moles of electrons that are getting transferred. You could look at oxygen going from 0 to -2 and say, okay, well, there are 2 oxygens doing that. Each oxygen atom is going from 0 to -2, so that's also a change of 4 moles of electrons total. So my delta G here is -4 times Faraday's times this E cell that I've calculated. 4 should have the units of moles here. And so multiplying all those things together, my delta G value here is -165,954 joules. You can turn that into kilojoules if you want, 166, or -166 kilojoules if you prefer. Now, we need to calculate K as well at 298. And now that we have G, I suppose we could calculate it backwards from here, but it's also pretty easy now that we have delta G. Right, we know delta G is -RT ln K. We can plug in this delta G, -165,954 joules equals -RT ln K, right? And now I can solve for K, rearranging all of this, divide by 8.314, divide by 298, and divide by, well, the negative will just drop out on each side. I'll have 165,954 joules divided by 8.314 divided by 298. And all of that is going to equal ln of K. I need to take E to both sides to get rid of that ln. So here I'm actually rearranging the formula, and we've talked about this formula before. K is E to the negative delta G over RT. That's essentially what I'm doing here, E to the negative delta G. Delta G was negative, so that negative sign in front of delta G makes it a positive 165,954 joules divided by RT. Plugging all that in, I get a K value of 1.23 times 10 to the 29. Remember, our equilibrium constants have no units. Okay, so that's my 2 answers for the first part, calculating the delta G and K for this first reaction. We're also asked to calculate it for the reaction below. This is the same reaction, it's just divided by 2. Remember, changing these coefficients doesn't change our cell potential. Our cell potential is still going to be 0.43. But now delta G only involves 2 moles of electron. Silver is still going from 0 to +1, but now there's only 2 silvers. So that's 2 moles of electrons times F, our constant, times the same 0.43 volts. Plugging all that in for this second reaction, I get a delta G of negative 82977 joules. Not surprisingly, it's half of what we got up here because we divided the reaction by 2. Now our K is e to the negative of that delta G, 82977, divided by RT. The temperature is still the same. And plugging all that in, I get a new K value of 3.5 times 10 to the 14th. Okay, so that's calculating delta G and K using these standard reduction potentials to calculate a cell potential and plugging them into these formulas. Use whatever formulas here you want to get between G, E, and K. Doesn't matter, it's all the same math, it'll get you there. This is just one way to do it. Okay, and realize again here that the coefficients won't affect the cell potential calculation part, but it does affect calculating delta G and then also in effect K as well, because the moles of electrons here are involved. Now, one final concept we have to discuss is the Nernst equation. And this can look a little overwhelming, but you remember when we first discussed delta G, we talked about it with these degree signs. We've talked about cell potential thus far with this degree sign as well. And all of that means is we're thinking about this chemical reaction under standard conditions. That means it's at 1 atmosphere, and all the gases that are involved are at 1 atmosphere. And it means all the concentrations of anything in an aqueous solution, the concentration, maybe like zinc is involved or something, zinc 2 plus aqueous, all the concentrations are 1 mole. Okay, so this delta G here that we talk about when it's standard is assuming standard conditions. All the gases are at 1 atmosphere, all the concentrations are at 1 molar. But like life doesn't always happen with all concentrations being 1 molar. Right? It's important to like tabulate all of those and have a table of everything standardized to 1 molar, but then you can change to your exact experiment. And that's what this equation did for us in the past. It said, okay, assuming everything's 1 molar, this is the delta G from some table for a given reaction. But if I'm actually doing this at 2 molar or a different atmospheric pressure, I need to consider this fudge factor over here, Q, where Q is still just like K, but not necessarily at equilibrium, products over reactants. And what are the exact concentrations here? They're not 1 molar, so plug them in, calculate Q, take the natural log, multiply by RT, then add it on to this standard state 1 to get your true Gibbs free energy for your specific reaction at your conditions, where it might not just be 1 molar in 1 atmosphere. So this equation was used to account for these non-standard conditions. And similarly, we're going to have to be able to do the same thing for our cell potential. And since we know delta G is negative NFE, we can just plug that in here for these two delta G's and effectively turn it into this equation for electrochemistry. And this is known as the Nernst equation. We can look up from our standard potential tables and calculate E cell. That is this right here from the table. That assumes everything is at 1 molar. But if my half cells and my beakers here that I'm running this electrochemistry in isn't necessarily everything at 1 molar, well, then I have to take that cell potential and adjust it. By how much? Well, it depends. What are the products and reactants of the reaction involved? write that expression of Q, plug it in here, take the natural log, and augment it with R and T and the moles of electrons and Faraday's constant. Now, you'll see multiple versions of the Nernst equation. These are all the same. They will all give you the same answer. Sometimes it's natural log, right, which is base E. Sometimes it is log log, which is base 10. Sometimes all these constants are wrapped together at 298 to give you something like this. Okay, I mainly stick to this first one because I like to keep track of all the units and just plug in R and T and N and F myself and work with the natural log. Okay, but any of them should do, assuming your temperature is 298. If it's not, make sure you're using one of these two top ones where the temperature is explicitly stated. Okay, that's why I recommend this first one. Now, let's see a practice problem where we have to use this Nernst equation. Here in part A, you're asked to just calculate the cell EMF, or cell potential. Remember, these are the same thing. EMF is the same as E cell. Calculate E cell for this reaction using the reduction table values, right? That's the standard E cell. That's what we've done thus far. That should be straightforward. Part B is then to use the Nernst equation to adjust when the concentrations aren't all 1 molar, but instead nickel is 30 times the concentration of zinc. All right, so you'll have to figure out what that represents in terms of Q, and then calculate and plug that in your Nernst equation here. So feel free to pause the video here and try to answer these before I solve them. Okay, so the first part is straightforward. Let's just find what is being oxidized. Zinc is going from 0 to 2 plus, losing electrons, oxidized. Nickel going from 2 plus to 0 is being reduced. Cathode, it's this one. So we're going to do cathode minus anode to get my cell potential here. And here I get 0.48, positive 0.8. So this is spontaneous, right? Would correspond to a negative delta G, for example. Okay, so that's part A. E cell is 0.48 volts. Part B now is we're told the concentrations here are different than all 1 molar. So now we're going to use our Nernst equation to calculate the EMF, or E cell, not standard state, but when I have different concentrations. I will use the standard state 1, 0.48 I just calculated, but I need to adjust it by minus RT over NF times natural log of Q. Right, so this E cell is the one I just calculated. Okay, the R here, 8.314. The T here is given in the problem as 298. The moles of electrons here, N, well, go back up. Zinc is going from 0 to 2 plus. There's 1 zinc, so that's 2 moles of electrons, N is 2. And Faraday's constant is 96485. And so we have everything we need except Q, right? Q represents products over reactants, right? So the concentration of zinc 2 plus over the concentration of nickel 2 plus. Remember, we don't care about solid things in our Q or K designations, so it's just aqueous product over aqueous reactants raised to their powers, but their powers are 1, so it's just zinc 2 plus over nickel 2 plus. And I'm told the concentration of nickel, the denominator here, is 30 times the numerator. So this just represents a 1 to 30 ratio. So Q here is 1 over 30. So now I can solve for my E cell. It's natural log of 1 over 30 times 8.314 times 298 divided by 2 divided by 96485. Okay. And all of that here in the second half of the equation should be negative 0.0437 volts. My ESO was 0.48. I'm subtracting negative 0.0437, so I get positive 524 volts for this non-standard state cell potential for this particular redox reaction I'm doing in some voltaic cell. Okay. We'll end here just by saying the importance of voltaic cells and some applications of them. Remember, electrochemistry can be applied as batteries. And so these voltaic cells are these just little, or batteries are just these little portable voltaic cells, right? So inside this battery, there are like two little half cell things going on, right? And something's happening over here and something's happening over here. And when you plug this battery into something like a flashlight, there's like a little metal prong here, right? That connects to a wire that goes to the front of the flashlight, right? And then the wire comes back here and plugs into the other side of the battery, right? You're putting this battery into a compartment where there's a little metal thing here, a little spring connected to a wire, and there's a little metal thing here that's also connected to a wire. That wire goes to the light. And so when you connect this wire, the electrons flow from anode to cathode, light the light bulb, and that's how batteries work. Now, they can be primary voltaic cells that can't really be charged, or you can have fancier batteries that allows you to, after some chemistry has happened, reverse the chemistry by pushing the electrons back the other way, and that is really the subject of electrolysis that we will cover in the next lecture. So that'll do it for this lecture. See you next time.